Okay, today we're talking about acids, bases, and electrolytes. So electrolytes are solutions that produce ions and are able to conduct electricity. Remember, electricity is just a movement of electrons, and electrons are able to move through a solution more when there's particles that have a charge, right? Remember, ions are just atoms that carry a charge. So how does this happen? Well, let's take a look at a couple of dissociation reactions. Now, these are pretty straightforward. When we have an ionic compound, right, what we have is a solid like NaCl, which is sodium chloride. And when that dissociates, what that means is that it separates, right? It separates into its two respective ions. So the first ion that forms is going to be the sodium plus ion, right? And the other ion that forms is going to be the chlorine 1 minus ion. So in a dissociation reaction, what we have is we have a solid structure, an ionic compound, that separates into its two positive and negative ions. When you have ions in solution, that's when you're able to conduct electricity. Ionic compounds do this everywhere, right? So when you look at something like calcium chloride, the exact same process happens. You separate calcium chloride into calcium, which is a 2 plus, and you create the chlorine ion, which is a 1 minus, right? And you have a dissociation reaction. Now, all of these are going to be in solution, so they're going to receive the aqueous symbol, right? But that's basically what dissociation means, right? Dissociation just means that you have a separation of individual ions in solution. Now, in the reaction, they're being dissociated because they're becoming hydrated. Now, what does hydrated mean? Hydration is the process where water molecules will surround the ions and dissociate them from one another. So basically, this is what happens when something dissolves. Okay, so let's take a look. All right. So we've already said that dissociation is the separation of ions in solution. Let's take a look at what a structure looks like. So here we have a basic crystal lattice structure of what sodium chloride would look like. You have your positive, you have your negatives. They're all combined in this lattice, right? This crystal lattice. Now we're going to pour that into a solution. So what's happening, right? This goes into the solution. Let's take a closer look and see if we can zoom in a little bit. So when you have a solution, what happens is that these crystal ions, right, this lattice is going to begin to separate. It's going to separate into your negative ions, right, and your positive ions. So here's your negatives, here's your positives, right? These are going to be free-flowing in solution because they are able to carry this charge, then they're able to help move electrons through, right? They're able to conduct electricity. Now, if we take a closer look and we're able to see exactly what's happening, here's what's happening, right? The water molecules here, right, are surrounding each ion. So the negative oxygen on the water molecule, right, because this is the negative, remember, water's polar, is going to be attractive to the positive of the sodium. And exactly the reverse, where the negative half of the water, right, or the positive half of the water, sorry, is going to be attracted to the negative part of the crystal lattice, which in this case is the chlorine. So by this water molecule surrounding each individual ion, right, that's what we call hydration. It's being hydrated, and that's how water is able to dissociate solids into their individual ions, right? These have become dissociated because they're hydrated. This is what I'm talking about. This also happens in compounds that have polyatomic ions. So for example, let's say we were to look at something like sodium sulfate, right? If this was to dissociate, the same process would happen, right? Sodium would separate into its ion, and then you would have the sulfate ion become apart, right, to form another ion here. So the dissociation happens whether you're working with polyatomic ions, monoatomic ions. The process is the same. Dissociation just means that you're breaking down from a solid into individual ions. Now, ionic compounds, we know this, right? Ionic compounds are always going to ionize because they're made of distinctly positive and distinctly negative compounds or ions, right? So when we're looking at an ionic compound, right, those are really easy to understand that they're going to dissociate and they're going to ionize because they're formed with ions to begin with. So if you were to hydrate them, right, then you're going to basically just take apart that lattice and reform ions, right? It's going to break down to form the cations and the anions in the solution. Now, feel free to pause this if I'm going kind of fast because I'm trying not to make a long video. Ionic compounds are not the only compounds that produce electrolytes, right? Now, typically, covalent molecules don't produce ions because that's not how they bond, right? Covalent molecules or molecules are not formed based on a positive and a negative charge. They're formed based on electron sharing, right? So, for example, sugar, when dissolved in water, is not going to produce ions. Remember, sugar is a molecule, right? It's a covalent compound. There's no metals, so there's no distinct positive. There's no distinct negative, right? So, when hydration occurs in sugar, it happens a little bit different. Here is an example of a sugar molecule, right? So, a sugar molecule is going to have parts of it that are positive and parts of it that are negative, right? And that's going to be where the water attaches itself to, but it's not going to break apart the sugar molecule. What it's going to do is going to take apart one of these molecules entirely from the crystal structure. So because you still have all this stuff in here, right? All these molecules, all these elements, right? You're not forming distinctly positive and negative ions. So sugar is a relatively poor electrolyte because it separates one of these molecules pictured above from the crystal structure, but this molecule stays intact. So because this one has so many positives and so many negatives, it doesn't really have a distinct positive and a distinct negative to make it polar. So because it doesn't have that positive and negative distinction, it doesn't really conduct electricity that well. So in this situation, right, even though it does hydrate and it does dissolve, it doesn't conduct electricity well because it's dissolving one of these entire molecules, right? You don't have to draw this. I just wanted to show this as an explanation. Now, acids and bases as electrolytes. Ionic compounds are not the only substances that can produce solutions that conduct electricity, right? So let's take a look at hydrochloric acid, right? HCl. We know that this is a covalent molecule, right? This has a metal, all nonmetals, right? This is electron sharing, so there's no ions here, right? And if I was to draw the Lewis structure of this compound, it would look something like this, where I have the electrons being shared here, and then chlorine is going to have all of its electrons that it brings with it, right? So the Lewis structure of this compound will look something like this, right? Again, this is not a positively charged cation being attracted to a negatively charged anion. What's happening here is hydrogen and chlorine are sharing these two electrons right here. And you can see that from the Bohr model that we have. So if I was to zoom in a little bit more, right, and look at this overlap space in here, what we're seeing is that those electron clouds are being overlapped and the electrons in there are being shared, right? So that's kind of what we see when we have a covalent compound, right? So there's the hydrogen electron cloud, and then there is the chlorine valence shell cloud, right? So again, all nonmetals, right? Covalent compound, no ions to speak of, right? So these electrons are being shared. So let's take a look at what's happening, right? If we were to draw the Lewis model, which I already did, right? I'm going to do it a little bit neater, right? It's going to look hydrogen and then chlorine. The electrons here are going to be shared. This is the covalent bond that I'm talking about. And then chlorine is going to have all of its valence electrons. So here's the Lewis model, right? In another version. Now, what happens when you have something reacting with H2O? Right? Let's say you have hydrochloric acid, which typically exists as a gas, right? And you react it with water. Well, what happens in this situation, right, is this hydrogen is going to react, and this hydrogen is going to come over here and bond to the water, right? Now, when that happens, then you form what we call a hydronium ion. So what's happening here is this hydrogen comes off as a hydrogen with no electrons, right? So now it's coming over as just a proton, a positive, right? You'll see this referred to often as just a proton, because if hydrogen loses its one electron, then the only thing that's really left is the single proton. So you'll often see hydrogen referred as a proton. So you'll see a proton is being moved over to water, and it's going to form this hydronium ion. So what does that look like? Well, 1, 2, 3, 4. Here's water, right? And then this one, this hydrogen coming over is going to bond here. Now, when that happens, right? When that happens, then this means that somebody's carrying extra, which is going to give it a +1 charge, right? Then the chlorine ion is going to go off by itself, and it's going to become a negative ion because, remember, it still has that extra electron that it shared with hydrogen. So now we see that this hydrochloric acid, right, is basically recombining to form this positive ion. Remember, this is a cation now. And this negative ion, which is your anion. So because this forms two ions in the process, not really with dissociation, but with a rearrangement of matter, right, then you're able to produce an electrolyte, because now, since this has a distinct positive and a distinct negative, you're able to conduct electricity, which makes it an electrolyte. Basically, to summarize, an acid is a compound that releases hydrogen protons or hydrogen ions in solution in the form of a hydronium ion. So it actually forms the ion, it doesn't release the ion, right? It actually forms that +1 ion when it becomes hydronium or H3O. A base is a compound that dissociates to release OH ions in solution. So what does that look like? Well, if you look at the hydrochloric acid example, right, you're seeing that a hydrogen proton is being moved over and bonded to the water to make hydronium, right? We see that here. Now, what happens in a base, right? Remember, a base is going to be anything that has this one. So this OH is going to make it a base. Whoop. Now, pay attention to this compound, because this compound clearly see that we have a metal, right? Because we have a metal, NaOH is actually an ionic compound. So this is an ionic compound. Why? Because it has a metal. Na is metal. So in this case, this compound will completely dissociate, right? It's going to separate into its two separate ions. You're going to form that positive sodium, and you're going to form that negative hydroxide. So a base works in the same way that it releases or it dissociates to create the positive and the negative ion. The difference, though, is that this compound is going to dissociate, meaning it's going to separate into its two ions, as opposed to the acid that's just going to form a new ion, right? So when you're talking about an acid, right, or a base, a base is going to be an ionic compound. The ionic compounds are going to form electrolytes because they're going to separate into those two separate ions. Now, depending on how much they separate, right, or the level at which they can separate is going to determine how much of the compound is ionizes or dissociates, right? Like how much of an ability it has to separate and make these ions. Now, depending on how much it's able to release is going to determine whether or not it's a strong or a weak electrolyte. So a metal hydroxides, like we just talked about, are basically ionic compounds, right? It's going to separate to the metal and to the non-metal. Like if we take a look at something like lithium, lithium is exactly the same thing. It's a metal hydroxide, so that's going to separate into lithium, right, which is a 1+ ion, and it's going to separate into hydroxide, right, which is a 1 minus ion. So because this is ionic, right, and it has a metal in the lithium here, it's going to just separate into the positive and negative ions, right? 100% dissociation, right, equals a strong electrolyte. In this case, since we're working with a base, this is going to correlate to forming a strong base, right? The reason it's considered a strong base is because it goes 100% into its two separate ions, lithium and hydroxide, right? So the more ions they're able to release, the stronger the electrolyte, right? The more ions you have present, the better conductor you are going to be of electricity. So if you're a strong electrolyte, that correlates to be considered a strong base. Acids are molecular compounds. They're not ionic, right? But remember that they form that hydronium ion. So if I was to combine an acid like hydrobromic acid with water, then the solution that forms is going to be a positively charged hydronium ion, which is the H3O, right? And you're going to separate that bromine to form that 1 minus, right? And when that happens, right, then you get a distinct positive and negative. Now, remember, this is not technically considered dissociation because all you're doing is you're moving it here, right? That hydrogen proton is being moved over. So you'll hear people refer to it as, it's completely dissociated. And it is separating the hydrogen from the bromine. But the reason it's making the positive is because it's bonding here, and this one is left without its partner. So in this situation, right, 100% dissociation, right, means that you're releasing more ions in solution, which correlates to having a strong electrolyte. Remember, more ions equal better conductor, right? And if you're a strong electrolyte, this correlates to be considered a strong acid. When ionization or dissociation are not complete, ions are less abundant. Therefore, they will not conduct electricity as well. So if you're not able to 100% separate or dissociate, then you're not going to produce a whole lot of ions. If you're not able to produce a whole lot of ions, you're not going to be a great conductor of electricity, right? So we call this incomplete dissociation a weak electrolyte. A weak electrolyte can be either a weak acid or a weak base, depending on how well or how poor an acid or a base are able to dissociate in water. So let's take a look at an example. Here we have acetic acid, which is basically an acid because of this guy right here. You have a hydrogen being bonded to the polyatomic ion acetate. Okay. Now, when this reacts with water, it's going to move the H over here, and you're going to form, again, that hydronium ion. And then you're going to leave that acetate all by itself, right, back to its polyatomic ion form. Now, what you can see here is that you were able to create this positive and this negative ions, but take a look at acetate. Acetate is still mostly together, right? So this is not dissociated, right? Because it's not really dissociated, it's still whole as an acetate. The amount of ions that are released are not going to be that many because look, acetate really only has that one ion to give away, and anything else that can be broken apart here, this is staying intact the way it is. So because this is not completely dissociating into all its separate ions, we call this an incomplete dissociation, right? So because this is an incomplete dissociation, right, this is considered a weak electrolyte because there's not really going to be an abundance of ions present. And if it's a weak electrolyte, then it's going to be a weak acid. Right? Same thing happens with NH3, right? In this situation, what happens is the water then is actually going to move its hydrogen over this way. In this case, water is behaving more like an acid. So what's going to form is you're going to form NH4, which is the ammonium ion. And then you're going to be left with OH, right? Because now you've taken away one of those one of those hydrogens. So in this case, you're not getting complete dissociation either. This guy's still pretty much together and this guy's still pretty much together. So you're not going to have an abundance of ions. When this happens, this is also considered a weak electrolyte. But because this one, the ion that's being produced, the negative ion here is the OH, right? This is also considered a weak base. Right? Now, as ions continue to form, right? Eventually, you're going to have a lot of ions. As those ions continue to form, those ions are going to start crashing into each other, and it's going to start to reform the acids. So you have a couple of reactions that happen, right? So the forward reaction, for example, is acetic acid reacts with water to form a hydronium ion with acetic acid, right? Or the acetate ion. Now, when those ions become abundant, the reverse reaction happens where the reaction moves in the direction to the left. So you have one moving forward, one moving to the left, one moving to the right, right? And eventually this is going to reach a point where these reactions are just kind of going back and forth. When that happens, we call that equilibrium. And how do we represent equilibrium in a chemical reaction? Well, equilibrium just says that the reaction flows to the right, to the products, and it flows to the left, to the reactants. And we represent that with a double arrow. So what happens is, as those ions begin to kind of crash into each other, then the acid and the water reform, right? So the reaction happens in both directions, and we represent that with double arrows, right? So all acids are going to do this, are eventually going to reach equilibrium where we have a balance where it's going back and forth, right? But the basic definition that we're going to take away today is the Arrhenius model of acids and bases. The Arrhenius model states that acids release hydrogen ions and base releases hydroxide ions. Okay, this is going to be the first definition that we have of acids and bases. We're going to cover two others in the days to come.